right, welcome everybody to the third day of the BioMedVis spring. So we have many interesting talks today. So let's get right started with the first talk. So the first talk is by Ingrid Hotz and Vijay Natarajan about the foundations of topological data analysis for the BioMedVis domain. Ingrid is a professor in scientific visualization at the Linköping University in Sweden. She received her master's degree in theoretical physics from LMU Munich in Germany and her PhD degree from the CS department at the University of Kaiserslautern in Germany. Since then, she has spent some time at the University of California, Davis, at the SUSE Institute in Berlin, and at the German Aerospace Center. Currently, she leads the scientific visualization group at the Division for Media and Information Technology at Linköping. Her research interest lies in the area of data analysis and scientific visualization, ranging from basic research questions to effective solutions to visualization problems in applications including flow analysis, engineering, physics, and medical applications. And Vijay Natarajan is the Mindtree Chair Professor in the Department of Computer Science and Automation at the Indian Institute of Science in Bangalore. He received his PhD in computer science from Duke University and holds a bachelor degree in computer science and a master's degree in mathematics from BITS Pilani. His research interests include scientific visualization, computational geometry, and computational topology. In current work, he's developing topological methods for time-varying and multi-field data visualization and studying applications in biology, material science, and climate science. Thank you both for coming today. So I'll hand it over to you guys, and thanks for your talk already.
Thank you for your introduction. And welcome to my lecture. So in contrast to some of the announcements, I'm not talking about topological data analysis, but rather about giving introduction to vector field visualization and biomedical applications. To a certain extent, this could be understood as a continuation of what Stefan started yesterday with an introduction into basic concepts of the visualization of spatial data or field data. So we have seen a lot of different types of data over the last days. So therefore, I would like to start with a brief clarification about what kind of data we are looking at. So as I mentioned, I'm looking at vector fields, and this contains as well first the word field. And field, this means that we are actually looking at some data that is given over some continuous domain, similar to what Stefan had yesterday, something that you have in a CT image, for example. But in our case, we will not have scalar data, but we will kind of have vector-like data that is given in some spatial domain. Sometimes it's also, in addition, time dependent. Despite the fact that we have some continuously given data, for sure, the realization or how we get the data is in a discrete format. So if we get our data from imaging devices, we will have it in form of voxel data, but in many cases, especially for flow data, the data comes from simulations, and then we can expect that we have a much more complex data structure. And as you see here in the image, where we have a lot of tetrahedra filling the space, in many cases, this is even a mix of tetrahedra, prism, and other data structures. This means you somehow need a way to interpolate in your data to kind of to fill your entire space with your data. The attributes that we are talking about, meaning the data that is given at every vertex, these are vector data, mostly given as an n-tuple. In our case, this would be three numbers, the three components of our vector fields, the x, y, and the z component, which can also be time dependent. So now before I start looking into different visualization concepts for flow fields, I would like to introduce a data set that you will see very frequently during this talk. And this is a flow around a cylinder. This is a very simple data set on the one hand side. On the other hand side, it also contains a lot of patterns and structures that are very typical for flow data set. And what you see here is kind of a box with simulation data and the flow is coming from the left, entering the volume, and then there's a cylinder, which is an obstacle for the flow, and behind the cylinder there are these vortices forming something that is also called the Van Karman vortex street. So the first visualization possibility, maybe the most direct way, is to show the flow just as errors or as cliffs. And here on this image, you see kind of 3 different cliff representation of one slice of the data set that I introduced before, the flow around the cylinder. And here on the top image, this is a very sparse sampling. You can immediately see that the sparse information does not really tell you much about the flow. In the center, you have kind of the regular sampling of a flow, which gives you already a little bit more information, but it's also dominated by sampling artifacts. And the last image really shows an error in every grid point. And here you don't see anything about the flow anymore. The only thing that you really see here is a simulation structure of the grid, basically the density of the grid. You do not even see how the grid structure really looks like. So this means error plots are mostly useful just to give a very first overview or to debug your data, or if you want to probe a specific position and want to know how the field looks like in this position. But there are also some examples where these cliffs are really used. Here's an example for electric field visualization in the heart. And the advantage kind of this cliff visualization is that it leaves a lot of space to use other visualization methods to encode other data. As here, for example, the color is used to show the electric potential, and the cliffs just give you an idea about the electric field. So the next step to get a little bit more continuous representation from the cliffs would be to try to connect these errors in a way that they form lines. This is again, here is a flow around the cylinder. On the top image, you see again the same pictures that we saw before. So in the background, I have a color mapping of a derived scalar field, which helps you a little bit to orient with this sparse representation. On the bottom, you see kind of the same picture where these lines are kind of connecting these vectors that you have in the picture before. And these lines are called streamlines. These are lines that are tangential to your vector field in every point. So this is here an example in 2D. For sure, you also can do this in 3D. On the right, you see here an image of streamlines in an aneurysm, and a plug flow in an aneurysm. And on the left side, you see kind of formal definition. What is a streamline? I think what is important here is streamline is a curve, and the curve is parameterized by some value S here. But the most important thing is kind of the bottom line, which tells you that the derivative of your curve should be parallel to the vector that is given in the respective position. So streamlines are used very, very frequently for visualization of flows, but not only flows, also for other fields, like here, for example, the electrical field. This is a medical application here, where the electric field is used as a diagnostic tool in a cardiac application. And you see kind of here very nice that these electrical fields are kind of starting in the heart and how they are distributed over the body here. The main challenge when using streamlines for visualization is the challenge of seeding. This is very similar to what Anna said in her talk about DTI. So if you do it in a naive way and you show everything, like here in the left picture, This again a flow through an aneurysm. It's a blood flow. You basically don't see much. There are a lot of lines, maybe spaghetti. And what you see on the right side is something that I call now a feature-based seeding. This is using an optimization method where streamlines, there's an optimization criterion, or the goal function is here to find streamlines that are especially long. And such a criterion really prefers areas where I have a lot of swirling. And so you get a nice representation of the vortex core inside of your aneurysm. This is a very simple criteria right now, just looking for long streamlines. You also can look at other criteria, as for example, in this picture here, where the criterion is that streamlines should be shown that are getting very close to the surface of your aneurysm. Because this is often interesting to see the impact of the flow on the wall of the aneurysm here. And these are two different examples where different areas of the surface of the aneurysm are favored. So there are a lot of extensions of streamlines. So there are one way that you just do not render just simple lines, but you render tubes or ribbons, or you even extend it to surfaces by not just having one seed point, but having a couple or a line of seed points and connecting them together to form a surface. This gives you a lot of free parameters here that you can use for other purposes. This might be a color that you can put on your lines. You could also map some quantities on the diameter of your streamline, or you could even put some textures on these surfaces. So if you are especially interested in the flow on surfaces or on cutting planes, then you can go kind of one step further. So here we started with a sparse representation using errors. Then we have kind of a streamline representation. And now the kind of the most dense representation where we use every pixel in our image for your information would be a texture. But this texture is called the line integral convolution, or in brief, kind of a Lick texture. The basic idea behind the Lick texture is that you take a noise image and you take your vector field, and then you use some convolution kernel to smear your noise texture in the direction of the streamlines. And then you get kind of this dense representation of the field. So it's actually a very popular method if you're really interested in kind of in surface flow or in representation on a surface. I also have here an example for an electrical field. This is a slice through the brain where kind of this dense representation gives you an overview about the field behavior inside of the brain. So due to this density, this gives you a very detailed information about your field. For sure, it only works on two-dimensional surfaces. Another example where this texture is applied on a surface here now of an aneurysm shows you kind of the surface flow that you have here in the aneurysm. So all examples that you have seen so far, they're not considering any dynamics or any change in the field. This is just kind of for one snapshot. You say, how does my field look at the moment? And you get a representation here. And many of these methods are not very well suited if you really have a dynamic field. And this means there are a lot of visualization methods that are especially developed for dynamic flows. So for an electric field, this does not play so much of a role, but for a flow where you often have a very dynamic behavior, there are important differences between a static field and a dynamic field. It's not only that kind of the the dimension of your space is increased by 1. So you're going from a 3-dimensional domain to a 3+1, meaning 4-dimensional space-time domain here. It's also so that some of the things that we saw before, like streamlines, do not have a real physical meaning anymore. It's not really clear what they are supposed to tell you. They are not representing the real movement of particles. They will just really give you a very flat snapshot of a specific moment in time. And another challenge that we have is that often interesting flow structures are hidden behind a background flow. This can also happen in a static flow, but there it's more or less easy to remove the background flow, and then the patterns still show your flow features. So what you see here on the right, this is again the flow around the cylinder. On the top image, this is the originally simulated flow, where you do not see much. And in the bottom image, it's kind of the same flow, where we just removed the background flow. And then you can immediately see kind of these vortices that are developing behind the cylinder. But if you have a time-dependent flow, in many cases, such a background flow cannot even be clearly defined. And even if you define something, it's really hard to extract. And therefore, there are generalizations of these streamlines, specifically for dynamic fields. One example are path lines. It's also an integral line. It's very similar to streamlines. The only difference is that in every step that I move ahead, the field is adapted to the current time, so that I really follow particles over time. You can imagine that you take a lot of particles, throw them in your flow, they're all glowing, and then you switch on your camera and you wait some time. It's kind of a long time exposure, and then you see all the traces of your particles in the flow. Another way to generalize streamlines are so-called streak lines. These are lines where you inject particles at fixed positions, not all over the place, but continuously over time. So both of these methods have their analogies in experiments. So what you see here on the bottom is really a place where you have ink that is released into the flow, which gives then some traces here. Both methods are pretty powerful. In the following, I will only talk further about path lines and try to tell you some of the conceptual difficulties that you might have with path lines. So at first we can look at the definition of a path line. Maybe you don't remember what you saw before, but it's almost exactly the same as the streamline definition. The only difference is that now my parameter is not a random parameter that as we had before, but it's a time parameter. And if you look in the bottom line, now we have here an explicit time dependence of our vector field. So if you think about what a path line actually is, so here we have a picture with one path line. So this is the geometry that you see here is the left ventricle of the heart. So this is just showing one single line. And here now the color of this line represents the time in the cardiac cycle. So since this is kind of a periodic movement, you move from yellow to blue, and then you jump to yellow again. So therefore you have kind of this discontinuity in the color here. But what this tells you is that every point on this line refers to a different point in time. So this is really a temporal summary that you see here. In reality, you would never see something like that, except if you have something like this long time exposure. but this is really a summary representation here. And to be able to understand this a little bit better, so we introduced kind of here an haptical pen that you can use to navigate time. And you put this pen is attracted to this line, and you can move this pen forward and backward. And while you are doing this, you're kind of changing also the time of your observation. And this is important for the reason that also the geometry changes over time. But what you see here in this image is just one random geometry of the ventricle. But this is not the shape that the ventricle has over the entire time. In most cases, people would pick kind of the largest extent so that you can at least ensure that the geometry contains your entire path line. But this, but the geometry is still changing. And here on the next slide, you see kind of how when you are moving with your pen along your streamline, how the geometry of the heart is changing here, depending on where you are. And as a reference, we have also here a plot of the volume of the ventricle with respect to the cardiac cycle. And this little bar going from top to down tells you where in the cardiac cycle you currently are. It's not only that path lines give you a kind of a summary over time. One consequence here is that path lines can also intersect. It can be that different particles are at the same point at different points in time. So this means that your path lines are also intersecting. And as we saw, even the streamline was already a mess before, but for path line, kind of, if you plot it all, it's even, the mess is even worse here. This problem is sometimes approached by trying to cluster path lines, to group path lines together, which are similar. The major challenge here is, so what do we consider as similar? When are two path lines similar? So there are different ways to look at it. You could either think about path lines as similar when they're in a close proximity and move together for a while. But you could also think about, I consider path lines as similar if they have similar curvature behavior or any other properties are similar. Whatever you pick, then you have to compute kind of distances between your path lines, and you get kind of a huge similarity matrix in the end. And then you can use any clustering method to group your path lines together. And I show you one example here. Also in the application, that's kind of the same data set as we had before. We have the left ventricle here. These are 4 different patients. Each column represents one patient. And for all patients, the same clustering method is used. And you get somehow similar behavior between the different patients, and you get similar clusters, but it's still not really clear what this is supposed to tell you. And also defining the similarity measure contains a whole lot of different parameters. You have to think about how long should the path line be that I consider, what do I consider as similar, do I compare path lines to different times when they're passing at the same point, or only path lines that are passing the same point at the same time. So there are a lot of parameters you can have to play around with. So in our applications, our observation was that in any case, when we had an automatic method, we needed kind of some adjustment later off. And we got the best results when we were kind of combining an interactive method, like here using, for example, parallel coordinates for filtering and a clustering approach. Another common method for visualization of flows, of dynamic flows, is particle animation. This for sure only makes really sense if you do not want to show a static image, if you can look at an animation. However, here you have the same problem. If you do it in a naive way, you don't see anything, especially particles are staying in places where not much is happening. And also here you can try to highlight regions of interest. So what has been done here is kind of that every particle has some life energy, and this energy drops if the flow is boring, and then the particle disappears and only stays if something is happening there. So I see that I'm already pretty far in my time. But I think the most important part is still missing. It's kind of, I've been mentioning this, we are looking at regions of interest. We're looking at something important to show, or we are, here the question comes immediately up. So what is interesting? What is interesting in a flow? Often we refer to these regions or to these lines as flow features, features of interest. And it's not always very obvious what it is. Sometimes the domain scientists know, sometimes they don't. But we can observe that there are a couple of very common questions that you will encounter again and again, which can be somehow approached with a couple of features. And I selected here so some of the questions that I've seen mostly. The first thing would be, what is the mixing and separation behavior of your flow? An example here would be, so if you think about an ocean flow and you have some pollution, people might be interested in whether this pollution stays in a certain area or it's kind of transported all over the place. Other questions are related to transport efficiency, which is something that's very relevant, for example, for the heart. And vortex structures are connected to both of these questions. So I do not have much time left, but I just probably, let's see, I just start and see how far I get. So one way to tackle this question of mixture is kind of looking at coherent regions in the flow, kind of looking at regions where I really know that there are some boundaries that the flow will not leave. And this is something that can be tackled with the concept of vector field topology, where we have separatories that connect critical points. And here you see these brown lines that are connecting these critical points, and they form kind of closed areas which will never mix with anything that is around of it. This vector field topology builds on streamline concept, and therefore it's mainly meant for static flows. Also in 3D it becomes very complex, but there are some possibilities to extend it to time-dependent flow and just keep some of these ideas, either looking at separating lines or at coherent regions. And the method that looks at separating features refers to the finite time Lyapunov exponent, which really just seeds a lot of particles and measures how they diverge. And then we can just generate a scalar field out of it and define a color map and render this. And then we get really very nice pictures like here for the flow around the cylinder, where these blue structures here are structures where we have almost no flow that goes across these structures. So here we focus kind of on the separating structures. We also can look at kind of coherent regions, and this can be especially well investigated if we have something a flow in a tube, something that we have in vessels often, where we have a clear inflow area. And then we place just a plane in this inflow area and then measure how the particles passing through this plane would separate. And generate this way a kind of a map on this inflow area, showing you regions of coherent behavior. This is an example here for again a flow in the aneurysm. On the left, you see kind of this map where gray values mean we have a high separation and black regions means there's no separations of the particles at all. Now we see streamlines or path lines here in this in all areas where we have kind of a low value of separation, and then we get very nice clusters of path lines as a result. We can either represent all the path lines that have been seeded in this region, or we just can represent show representatives. The nice thing about this representation is, on the one hand side, you see that there are a lot of regions where have gray values, where have some separations, and these are regions that are not clustered, but probably it even doesn't make sense to cluster them. So this map gives you an overview about the overall coherence. And here we have kind of selected 4 points in this map, which are very, very close to each other in one of these gray areas. But each of these lines, which are shown here in this picture, have a completely different behavior. And here it might not make sense to cluster them in any regions. So the second feature that is of interest are for sure vortices. I will jump over that due to my limited time. I just show a picture, and this is probably the most well-researched area in flow visualization and flow analysis is how can we define a vortex? How can we extract a vortex? And without going into more detail here, I would like to conclude with my favorite flow visualization, probably. This is a visualization of a jet coming, also a flow coming from the left. And this is a very carefully designed visualization here, combining all basic visualization methods that we have seen before. We have streak surfaces here, we have path lines, we have even an isosurface rendering here of a flow, of a backflow, combining all important flow features in this flow. This is nothing that can happen automatically. So here you have to have a lot of domain knowledge to generate a picture like this. And I think really the art in flow visualization is to take these basic methods and put them together in a meaningful way. And sometimes I say, okay, these basic methods is like you are getting your letters, and now you have to make a story out of it to tell what's happening here. And this is what is a real challenge. Yeah. And as in all other applications, you also use your screen space in an efficient way. Try to get the most interesting out of your data. Yeah, and with this, I would like to close my lecture. And if you have questions, feel free to ask now or later at Discord.
Thank you very much, Ingrid.